Hello, everyone. Welcome to 2021. I'm Mark Crowley with the Waterloo Artificial Intelligence Institute here at the University of Waterloo, and we're happy to welcome you back to the beginning of our seminars for 2021. Brave new, happier year future we're hopefully all in. So hopefully everyone has gotten through the past difficult year, and we're moving forward together in this. So today's talk's going to be an exciting one from Dr. Mark Riedl from Georgia Tech School of Interactive Computing. He's the Associate Director of the Georgia Tech Machine Learning Center, and he's the recipient of the DARPA Young Faculty Award and NSF Career Awards, and has lots of collaborations with different companies and organizations. His work is in natural language processing, and in his description he has that he aims towards the development of artificial intelligence, machine learning technologies that understand and interact with human users in more natural ways, which is something we all greatly need. And his talk today is on the quest for automated story generation. So welcome, Mark, to the University of Waterloo virtually, and take it away.
Hey everybody, it's a pleasure to be here. I hope everyone is doing well. I understand you just started your semester. So hopefully I get to be the person who kind of kicks it off and kind of gives you some inspiring or at least amusing sorts of things to look at. So I'm coming from the state of Georgia in the United States at Georgia Tech, as Mark generously mentioned. And I run the Entertainment Intelligence Lab, where we like to look at this problem of human AI interaction in interesting and entertaining and aesthetic sorts of domains like storytelling and computer games. So we like to do serious work, but have fun doing it. So I'm going to talk today about automated story generation. I'm going to talk to you a little bit about why we want to have computers that can tell stories, that generate stories, fictional stories from scratch, and kind of talk to you about some of the ways that we've been trying to solve this really, really hard problem. So I'll explain a little bit why we should care about this problem in just a minute. I kind of start with thinking about humans, right? So when we think about humans, stories come up all the time, right? So narrative is a fundamental means by which we organize, understand, and explain the world. So we tell stories all the time, right? We tell stories to entertain, we tell stories to educate, our stories are in computer games, they're on our TVs, they're around our dinner table, right? So when we come home, well, assuming we ever actually leave our homes, right? We get together with our families, we talk about what's happened to us in our days, right? We're telling stories to each other to help us understand the context that surrounds us all and to share memories and to bond as well, right? So we call this narrative intelligence. There's this innate ability in humans to craft, tell, understand, and effectively respond to stories. So this is a very important part of the human experience. And my overall research objective over the last so long has been to figure out how can we instill computational systems with this narrative intelligence. Now, today I'm going to talk specifically about one type of narrative intelligence, which is automated story generation. So this is the construction, the fabrication of fictional stories that have never necessarily existed in the real world.
So Mark, just in case, I don't know, you can't have you see your slides yet. I don't know if you're putting them up yet or you don't.
Oh my God, you can't see my slides?
Yeah, I thought you were just doing an intro without them, but if sure.
Oh no, it had my screen red. No?
We're seeing your camera.
You're seeing what?
Your face. Hello.
You're seeing me. Slides now?
It's coming up.
Yep, we can see it now.
Okay. Weird, because I had the red bar around. Still seeing my slides.
Now it's full screen. Great.
Okay, so, all right, well, nothing really to see, right? Yet, so here we are, right? Talking about automated story generation, the creation of fictional stories. And why do we want to do this? Well, as I mentioned before, stories are everywhere. They're in our entertainment, they're in our education, they're in our everyday conversation, and they're, I think importantly, a means by which we share experiences, create rapport. So between humans, so can we create rapport with humans and computers? Can we generate effect? Can we get people to see things, feel things that we want them to feel? And there's also tied up in this a lot of kind of what I think of as fundamental AI research problems. So to generate a story from scratch, we're going to have to plan with language, something we don't necessarily know how to do very well in the broader scope of the AI and machine learning communities. We need to think about how computers can achieve communicative intent. So stories are messages. They often have messages. So how do we make sure those messages come out? They involve language understanding. So how do we manipulate these symbols that are called language, right, in such a way that we achieve communicative intent and we achieve the goals that we're trying to plan with our language? They involve lots of complicated problems like sociocultural and common sense knowledge. So these are tools that we use to tell stories. Humans use to tell stories that make sense, because if they don't have common sense, if they don't share social cultural information, they're hard to understand. So we need to make sure they're understandable by humans. And we have to have theory of mind, right? So it's not just about putting text to page. The reason why we tell stories in a particular way because we want them to be understandable. So how do we know whether our audience, the reader, is understanding and following what we're trying to achieve? So these are all really hard problems within natural language processing, within the larger, broader scope of the AI community. And the fun thing about automated story generation is we get to touch on all these fundamental problems, not just one at a time, but we kind of have to touch all of them at the same time while making things that are hopefully enjoyable and readable. And lastly, I'll say automated story generation, you can think of it as a creative evaluative task. So how do we know that our computer systems are understanding language? How do we know that they understand common sense? How do we know that they're appropriately applying theory of mind or planning correctly? Well, we get to see it, right? We see the text, the outputs, and it becomes pretty obvious when our computers don't understand what they're talking about, because our stories also don't make a lot of sense. So we can touch on all these AI things, and we can see how well our system is doing with all these things combined. Okay, so what I'll do next is I'll kind of talk about some applications as well. So, I mean, I think when we think about story generation, we think about the application of just telling stories. Well, maybe I want to generate a novel or a book or a bedtime story for my kid, right? So we want to be able to create text, obviously, that we can actually read, that is going to make sense, that is going to be entertaining and engaging to us. This is an output for one of my systems from a few years ago. I think it's a good one, so I'm showing it here. Now, it's not all about fiction as well. Stories also come up in serious applications like news, right? And there's been an increase in news organizations like the Washington Post that have turned to automated story generation, not to make fictional stories, but to take facts about things that have happened in the real world and lay them out in narrative form. So that's another form of AI storytelling. Other things that we can use story generation for is explanation. So as robots and other agents come into our world, whether it's healthcare robots or self-driving cars or Siri or Alexa or whatever it is, we often find that they don't do things exactly the way we want. They fail sometimes, and our inclination is to ask why. Why did that happen? Why did the robot do that thing that it just did? So if we step back and say, well, how do we make explanations? How do we make AI systems build explanations? We might say, well, how do human experts make explanations? And what we find is that experts often encapsulate their explanations into stories, little vignettes about what they're doing. And more importantly, users seem to really like it when these explanations are encapsulated in these little vignettes. So we can imagine in the future, as a self-driving car explaining what it's doing as it's driving down the road. We can also think about what I call machine enculturation, which is the encoding of cultural values into our systems. So human cultural values are implicitly encoded in stories. So if we teach our computer systems about these stories, we can have them mine these social conventions about the stories. And how is this a generative task? Well, by getting our AI systems or our robots to act consistently with these normative stories that encode cultural information, they tend to do things that reduce conflict. They tend to act in a way that reduces or matches our expectations, right? They do things more like us, and we're more comfortable with them, AI systems that act more like us. Now, I'm not going to talk about this particular type of generative system, which is more about the embodiment into AI agents. I'm of course going to talk just more like about the systems that are generating text. So we're going to talk about AI systems that generate readable text that we should see as stories. And I'm going to kind of break this down in three parts, largely kind of tracking with the main phases that story generation as a field of research has gone through. And I guess I've been around long enough that I've kind of touched on all these different phases. So I'll also mostly be talking about my own work as well as kind of a way of laying out how we've progressed in terms of this grand goal of building AI systems that can generate stories. And I think with all stories about AI, we're going to start with symbolic systems. So why are we even talking about AI story generation? It turns out that story generation has been one of the grand challenges for artificial intelligence virtually since we had the idea that computers can be intelligent. So AI story generation actually started with language understanding. Right, so at the very beginning days of artificial intelligence in the 40s and 50s, we wanted to say, well, humans, we're going to want to have to communicate and speak to our computers with language, and we want those computer systems to speak back to them. If you imagine yourselves in the 50s, you're saying, well, what are the good story or good language corpora we have? They were news and fairy tales and children's stories, which were perceived as being simple enough that early computers might actually be able to process them. And so a lot of early language understanding research was actually narrative understanding. And it didn't take very long for someone to say, well, let's go beyond language understanding. Let's try to do language generation, which became story generation. So even as early as the 1960s and the 1970s, we had researchers trying to generate stories. And at the time, they were simple systems like generative grammars and rule systems. They actually worked pretty well if you built these grammars and rules in a particularly interesting way. But what does it really mean for a computer to be an author? Well, again, we can look to humans and we could say what psychologists will tell us is that any sort of creative writing activity, whether it's writing a research paper, an essay, or writing a story, is a problem-solving activity. You have a communicative intent. You want something to happen in this document, whether it's a story or not. And now it's a matter of planning out the different steps to make your point. In a story, the point might be characters do interesting things or end up in interesting situations, right? But before we can go on, we actually have to make a decision here. What does it mean to make a story? Should we be focusing on words, on sentences, or should we be focusing on semantic constructs? So what do I mean by that? Well, here's two pieces of story, and they both mean more or less the same thing, but they're expressed in very different representations. Right. So the top blue is a semantic construct. There's this notion that Sally killed John with an umbrella. We can also think about that in terms of linguistic words, language, right? So we might express that exact same idea with the word Sally swung her umbrella with all her might. She knew that she would never be bothered by John's mansplaining again, right? So the implication that Sally killed John. Now, I think some researchers are going to prefer one way, the semantic constructs. Some researchers are going to go the other way and prefer words and sentences, which are obviously much more readable and much more enjoyable to read. And there's an interesting idea here that one of these has to entail the other, and that's an entire research problem itself. How do we entail that John was killed, even though the text in yellow never even says that? But for now, what we can basically say is when researchers start to work on story generation systems, they kind of pick the level of representation they want to work on. Do they want to work on more of these plot level events, or do they want to work on words themselves? In the early days, most of the work we did was working on these semantic constructs because they were much more easily processed. So this is about where I come into the picture. So some of my early work, my dissertation work, was trying to generate narratives as logical proofs. And we did go with this semantic construct sort of way. And the idea here was that a proof is basically a story. But it doesn't have to be P equals NP or anything like that. It can be about symbols being manipulated. So here's an example of a system where we might try to generate a Little Red Riding Hood story. And so what this graph is basically saying is we can tell a story by building this graph. And the blue boxes are the events or the actions that can go into a story. And you can think about selecting them from a big library of different possible actions. And how do we build this graph? Well, the graph can only be assembled in certain ways. So for example, we can't have Little Red Riding Hood tell the wolf about Granny until Little Red Riding Hood meets the wolf, and so on and so forth, right? So there's a puzzle to be solved. We have to put the pieces together. And what we're really trying to do is we're trying to find a sequence of actions, or this graph, that proves that the goal state, the outcome, can be reached from the initial state. So every one of these actions transforms the state of the world in a particular way, and we keep trying to transform the world until we get to the outcome. And the reason why this works is because actions have logical constraints. They have preconditions and effects. So preconditions basically is knowledge that's pre-coded into the system that tells us what is necessary. When can we use one of these blue boxes, right? So Little Red Riding Hood telling the wolf about Granny, we can only use it if the wolf is alive and the wolf knows Little Red Riding Hood. And of course, knowing Little Red Riding Hood is established by some action that has come before it. So we create these nice causal linkages, and then we have the effects, right? So once Little Red Riding Hood tells the wolf about Granny, then wolf knows Granny, which might be necessary for a subsequent action, and so on and so forth. So we have this process of finding this sequence that gets us to the outcome. Okay, and this turned out to be a very powerful technique because storytelling is planning, right? So if I can tell you what the initial state is and the goal state is, it's just a matter of filling out the details in the middle. But there's a catch, right? The catch is I have to do some domain knowledge engineering. So I have to tell it what the preconditions and the effects of all these actions are. I think of them as like Lego building blocks with complicated connectors, right? I don't expect you to read Lisp here, but to define the action of what happens when a monster eats a person in a fantasy world, right? I have to give all this information about, whether the character is asleep, whether they've already been eaten, whether they know someone, so on and so forth, and what happens when they've actually been eaten. I also have to give information about the initial state. Who are the characters? What can they do? And the outcome. What do I want the story to look like at the end? Right. But once I've built all this knowledge into the system, then we can basically press the play button and we can start to generate a story. And this is a story about Aladdin. But it wouldn't be fun to create the Disney version of Aladdin, right? So this is going to be the version of Aladdin where the evil vizier marries Jasmine and the genie gets killed. Okay, so this is the gritty Snyder reboot, I guess. I don't know. And I'm just going to kind of show you how this kind of graph gets built up over time if the system makes all the right guesses the first time through. But that's really not important. We don't want to read graphs. We can also turn this into language. So we templatize all those actions and we can get a tellable story, right? Something that we can actually read. Actually, this language is pretty bad because my templates are pretty bad, but you can kind of see that everything is well justified. There's a kind of a coherence to the story, and we definitely get to the ending that we wanted to. Okay, I'm not going to spend a lot of time on that particular system because, well, why were we not done in 2010, right? Did we solve all of story generation in 2010? We didn't. We built systems that could tell pretty good stories, but there's kind of this underlying problem, which is that we don't get any story unless I do good knowledge engineering. And once I've done all the good knowledge engineering of what characters can do, under what circumstances they can do, what the initial states and the goal states are, it's not particularly interesting, right? I do all this knowledge engineering and I kind of know what the story is. It's going to be. I don't know all the details, but I'm never particularly surprised by it. And so the issue is that I didn't want to be the person building the knowledge into this system. I would rather the system already get the knowledge that it needs to tell the stories, and I could just tell it what I wanted to tell stories about. So we kind of turned to the era of machine learning, right? And because what I really wanted to do, and what I think most people who do story generation nowadays really want to do, is what I call open story generation, which is tell a story about any topic. I just want to sit down with the computer and say, hey, computer, tell me a story about whatever happens to be a bank robbery, or going on a date, or a princess that rescues a king, whatever it happens to be, right? So the problem with the previous phase of story generation was we were tied to these micro worlds. I had to build all the knowledge about the world, and the computer system could never go outside of what it knew. And what it knows was very limited because it was what I could write down. And I was a very limited person, right? So Plus, most people can't do knowledge engineering anyways. Right, so the idea of open story generation was then we have to get an AI systems that can go acquire models of how to tell the stories about particular topics. Those models have to be good enough that it gets the details right. And then once we have these models, then we can operate on the model to create novel story content, and we can tell an infinite number of stories about many, many, many more topics than we'd be able to do with the classical symbolic systems. Okay, so first attempt at doing this, well, maybe if I just don't want to be the person doing the knowledge engineering, maybe I can get a crowd to do the knowledge engineering. Actually, you don't want to do that. You don't want to get a crowd to generate knowledge, but here's one way of going about building an open story generation system like I just talked about. We can go and crowdsource a bunch of example stories. So if I want a story about a girl and a guy going on a date together, I go and I get a bunch of examples from the crowd, 100 different stories about what happens when you go on dates. I compile this all together into some sort of model. In this particular work, it was a symbolic model. It doesn't have to be that, but it was. And then I operate on that model to tell the story and actually construct a novel set of words and a novel story that has never been told in any of the crowdsourced examples before. Kind of mixing and matching everything that people told me is possible in this particular domain. And I would say this actually worked really, really well. But it worked really, really well because of the crowdsourcing. So basically, every time I wanted to tell a story, I got a super specialized corpus of stories, and I pulled those stories apart and then recomposed them together in a novel sort of way. Now, the issue is this isn't actually an open story generation system. It can only tell one type of story at a time. If I want to tell a story about something else, a bank robbery, I would have to go get another crowdsourced example, set of examples, build another model to tell another story. So while I think this was actually a very powerful way that I think actually makes some of the best stories that I've seen from an AI system, it was very limited in the sense that it was reliant on really good small sets of data. Wherein what we really want to do, I think, and why we're all really excited about natural language processing and machine learning nowadays is corpora in the wild, right? I just want to go send a system out and just suck down tons and tons of knowledge from the internet and have that system learn everything it needs to know to tell a story. How to tell a story, all the domain topic information, all that is encoded on the internet somewhere. Can we pull that down and use it instead? So now large data, right? This is the big data formulation of story generation. And I think it's probably not any surprise to anyone here that we're now going to turn to things like deep neural networks. Specifically, we're going to turn to a type of deep neural network, which is a language model. And for those who are not familiar with that term, it just means we're trying to build a system that can approximate a distribution that says, given a token, I want to predict the probability of a token given a previous sequence of tokens. These tokens could be words or characters or even complete sentences, right? But the idea is let's predict something based on what I've seen in the past. And there's a couple different ways you can do this language modeling. You can use recurrent neural networks, which was kind of where neural networks started out with. More recently, you've heard about things like transformers. So BERT, and GPT-2, and BART, and many other things like that. Just more powerful versions of language models. Okay, so we're turning to neural networks. So let's try it. And I guess I'll say for just a second. There's going to be a little bit of a disappointing aspect to this because I'm going to talk about work that started circa 2016 or so, which was really before we had these large-scale transformers. So a lot of the work I'm going to talk about is using these older, I hate saying the word older, but the technologies circa 2016 that were superior were these recurrent neural networks, and you had to kind of train them up from scratch on corpora that you could find on the internet yourself. Now we have companies like OpenAI and Google who are building these massive language models, much larger than we can actually train on our puny little desktop computers in our labs, right? So what you'll see is kind of the technology getting a little bit better through the next sequence of slides. But circa 2016, what you would do is you go and find a corpus and you'd run it through a recurrent neural network and try to learn something to do. So here's an example of what happens when you take J.R.R. Tolkien's books, specifically the Silmarillion, and train a recurrent neural network on it, and then get it to generate. Okay, so then the hill of the south, and the south of the Ladiest, and the land of the valor, and they were slain, and they were there, and they were slain, and they were slain. Now, it turns out that this is actually a really good plot summary of The Lord of the Rings. But I jest, right? It's not bad. There's a lot of killing in The Lord of the Rings. What's it doing is it's picking up on the patterns that lots of characters, there's lots of this terminology of characters slaying other characters in The Lord of the Rings and the Silmarillion, right? And it's picking up that pattern, and it realizes the best way to get low entropy, low loss in this neural network is to use this word like slain a lot. And the South and the North is a big aspect of Lord of the Rings books as well. Okay, so I can actually do a little bit better than this. That was a low temperature. I can actually pump up the randomness of this, and we can regenerate, and we get something a little bit better, right? But the sons of the elves and the hour of the Vala, they were cold, not in their long lands. All right, blah, 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 right? It actually reads not horribly bad, circa 2016. The reason why, right, but you know, things did change, right? Maybe I just didn't have enough data. Maybe a few books from one particular author wasn't enough. Now we have GPT-2 and all these very large transformer models. Well, what if we can generate stories with these very, very large transformers that have seen gigabytes and gigabytes of text on the internet, including books? Okay, so what we do with these large transformer models is we give it a particular prompt. So the prompt I gave it is what's in black here. So the hungry dog licked her lips as she watched her owner eat, and then it just kind of continues from that point forward. She could see the white teeth of her jaw, then moving behind the right ear, the hunter picked up his sword, directing the dogs in the cloud of mutterings. Did you just feed the dog, et cetera, et cetera, et cetera. If you were to read through this, what you see is that the same thing is still happening here. The fluency is just a little bit better, right? So we started out with these concepts of dogs and lips and eating, right? From dogs and lips and eating, we see teeth and jaws. Those seem to be good probabilistic choices, right? They're very related to the words we saw before. Somehow we get swords thrown in here. I don't understand why, but dogs are feeding. Well, teeth and jaws might imply killing, and killing implies blood. Killing and dogs and teeth and jaws somehow convinces that the neural network that the word wolf is a good thing to talk about at some point. All right, she is one of the most dangerous wolves I've ever met. Now our dog has become a wolf. Why? Because probabilistically, wolf is a really good word to choose here, and it's not really thinking about the fact that it was talking about dogs in the past. So we still have this notion of patterns of words correlating with other patterns of words, but this doesn't necessarily make for a good story. Now GPT-3 will do better. It'll keep coherence a little bit longer, but it'll still kind of make these same classes of mistakes. So we have challenges. And a lot of these challenges come from the way we train our AI systems to tell stories, our language models. So one of the problems is that story corpora are somewhat unique with regard to other machine learning problems. Stories are about uniqueness. Every sentence transition in a story tends to be different from every other sentence transition in a story. And when people write stories, they want stories to be different than other people's stories. So what you see is over a corpus of just stories, you don't see the same things happening over and over again particularly well. You might see patterns of words and word usage, but you don't see kind of the conceptual repetition that you might want to see at the semantic level. So what is the right level of representation? Should we stick with words? We definitely see this pattern of word usage, and it gets us some pretty good stories, pretty good language, I would say, not necessarily good stories. Or do we really want to kind of look at this notion of plot progression, right? So in stories, every event kind of serves the purpose to move the story towards something, right? So maybe plot progressions are the ways to think about it, which are different sets of patterns that we might try to extract from language than words themselves. Now, all this is a data problem in some sense, because, well, how do we train these neural networks? What is the data that we train or fine tune our neural networks on? Where do we get plot information versus word information? So for the next little while, I'm going to talk about neural networks that were trained on Wikipedia plots, so we can scrape plot outlines from Wikipedia. And these are nice because every single sentence is more or less an event. So it basically says for certain sorts of corpora, sentences tend to also be events, but this is not the case when you try to read, Gone with the Wind or a real story or something like that. Okay, but here's the general idea, right? So we have a human, they prompt us with a sentence. Let's say John unwittingly unleashes an insidious pox. We have some sort of neural network that is a sequence-to-sequence neural network. It basically says I'm going to take one sentence and generate another sentence. We get a sentence out, so he crumples and is about to be husked. And then we can iterate through this process. We can take that sentence and we can generate the sentence after that and the sentence after that, and so on and so forth. Okay, so, pre-transformers and fine-tuning, this is kind of what you would have. You'd have a prompt and you'd have a story corpus of plots. And here is actual data from one of the plots in the story corpus that we've been using. And I do not know where this came from. I do not think it's Star Wars canon, but it is in our data set. Right, so R2-D2 carrying some drinks on a tray strapped to his back passes Yoda, who is using his force powers to hog the drinks. The next sentence in the plot corpus is Obi-Wan and Anakin are drinking happily, and Chewbacca takes a Polaroid picture of Anakin and Obi-Wan. Okay, now we train on that sort of corpus. We might take that R2-D2 sentence and say, well, what can we generate? Well, what we might generate is something like this. Can this block give him the advantage to personally run around with a large stick of cheese? And again, this is the same thing we've seen before, right? It's picking up on the idea of food here. Drinks and trays. All right, so maybe talk about other types of food like cheese, and carrying means running around. Okay, so this is both a horrible sentence, but also what sort of plot progression are we going here? Is this a good plot progression or is it not? It's definitely different from what the corpus said should happen. Maybe the problem is that we shouldn't be working on word levels. Maybe we should be working at a higher level of abstraction. And how do we get there? Well, what if we take this corpus and we pre-process it? Let's suppose we take all of these sentences, and in this particular corpus, remember every sentence is an event. And let's say there are 5 pieces of information that we really care about, and the rest is distraction. So maybe we just care about subjects, verbs, objects, prepositions, and helpers. So now we could take any story corpus and turn it into a set of 5 tuples. So now the idea here is that more of these unique sentences should map into this smaller space. We should start to see more pattern. We should see these events start to occur more and more again, because they don't, they're not written to look unique from other times in which things kind of share the same semantic space, right? So we're forcing everything into the same semantic space. And the theory is that we should be able to basically reduce cross entropy because we'll see more of these event patterns over and over and over again. Actually, we can do better than this. We can further generalize through WordNet or VerbNet. So WordNet is a resource, dictionary resource. And what's nice about WordNet is it tells us word hierarchies. So it'll tell us things like dogs are mammals, and mammals are animals, and animals are animate beings, and so on and so forth. And VerbNet kind of does the same thing with verbs. It tells us these verbs tend to mean the same thing than each other. So we can actually go one step further. We can take an entire story corpus and we can boil it down to word class, verb class, preposition, word class. So what the idea here is we're going to compress the semantic space even further so that more and more of our story tends to collapse down into generalized events that should be seen more often than unique sentences. Okay. So the idea then is take the exact same problem we had before, but convert it. Now we have a named entity carrying tray, carrying drinks, using force. What we'd expect to see is some drinking and some taking of pictures. And now we're going to ask, what does our neural network do with this new type of abstracted semantic space data? Okay, so this changes our pipeline a little bit. Now we take a sentence from the human, that same sentence as before, maybe John unwittingly unleashes an insidious pox. Now we eventify it. We turn it into an event representation that we hope we will see more and more in the corpus, and therefore be able to make better predictions about what happens next. Our neural network now takes this tuple and tries to predict the next tuple. Maybe it predicts the male spatial configuration 74 of the adopt 93. And if we train this neural network, what we see is that we get better predictive power. So here we're measuring perplexity. Perplexity basically just means how confused is the model about its own data. And so lower is better, right? So when we were doing word level prediction, what we had is readable, somewhat readable sentences, but the perplexity was really high. Basically, the system was sort of guessing words. Now we have the perplexity on events much, much lower because our semantic space is also lower, right? So we should expect our perplexity to go down. Our ability, we're still guessing, but we're not guessing as badly. And that's a positive thing. Except we don't really want to walk around reading stories about male spatial configurations adoptions, right? Actually, that's unreadable. I don't even know what that means. And I work with the data, right? So what we had to do then is make a second neural network that can take these events and make them back into sentences. And we do this in two phases. We generate them back into generalized sentences. So we basically just look at the corpus of events and sentences and how they match together. And we're trying to predict the sentence that would have produced that event, right? So we might get something like male crumples and is about to be sheath. So you can see kind of these slots where we have not made any sort of commitment to who the male is or what a sheath is. For example, because we want to give our AI system a little bit of flexibility, we want to remember characters like John, right? So who should the male be? The male should probably be John. So let's put these pieces of information that we stripped out of the story back into the story a little bit later, and we can finally kind of reconstruct the sentence we want to see before passing that back to our human reader. Okay, so now we have this new pipeline. Now it involves two neural networks, one that goes from event to event and one that goes from event and tries to reconstruct the sentences. And here's kind of an example of some of the things that we could do, around 2018, right? So the first one is obviously from Harry Potter. So he reaches out to Remus Lupin, a defensive dark arts teacher who is eventually revealed to be a werewolf, right? So again, this comes from a plot summary corpus. And the output is going to be something like when monster nemesis describes who's finally realizes male cannot, dangerously entity male was released from penal institution. Okay, so we didn't do the full stage of putting all the names back in here, but if you imagine the penal institution being Azkaban and the monster being the werewolf and the male being lupus, right? You can see how this might actually be not a bad output. The one on the bottom is the example we just did that comes from a computer game plot, actually. Okay, so are we making progress? Well, I think we're making progress, but we still kind of have this problem. And I think the problem is that these language models are approximating this distribution, right? What is the best token based on previous tokens? What is the best word based on previous words? Now, we have forced the AI system to do a little bit better by taking away a lot of words and focusing on these, subject, verb, object sorts of things. But it's still choosing events or these subject, verb, object tuples based on what we've seen in the past. But sampling from a distribution is an uncontrolled generation. It's backwards looking. We're saying the best word or the best tuple to choose now is based on what we've seen in the past. Now, I would argue that this is not how humans write stories. We don't write stories saying, ooh, I used these words in the past. I think this is a new good word to choose. I mean, there's probably some of that going on here, but I believe that story writers are also doing some sort of planning. They're forward looking. They're saying things like, I want this story to go in a particular direction. I want the heroes to win. I want the villain to be put in jail. I want the princess to be to rescue the prince. Or I want you to feel sad, right? So there's some sort of communicative intent. And how do we know that our story is going to go closer and closer and closer to that communicative intent? How do we know it's going to achieve that communicative intent when it's only looking backward saying, oh, you used words about wolves or dogs and jaws and teeth and blood. So the next reasonable thing to do is talk about this, that we don't have any guarantee that that's going to achieve a communicative intent. We're kind of flying blind here. So we wanted to fix that. We want to say, how can we give neural networks, these language models, the ability to do some forward look ahead? And again, this is an important idea in storytelling, because if we want to tell a story that kind of fits these classical patterns of storytelling, we are going to have to make decisions early on that set up later situations, right? So classic love story looks like this, right? So some characters meet, there's some unrequited love. One of them comes to admire or love the other. Admire is just the verb net word class for love. There's some sort of unfortunate discovery, then they come to an understanding and they resolve their problems and they get married, right? Classic rom-com sort of plot pattern, right? But the decisions at the beginning are going to set up how we end the story. So how do we make sure that a story that we generate goes through these plot points? Heck, how do we even just get to meeting? How can we guarantee the two characters are even going to meet in a story when we don't know we don't know if we're moving towards meet or not? Do we just get lucky, or do we try to force the neural network to make decisions that move towards one of these plot points? So what we're going to do is we're going to try to teach neural networks to be forward-looking. And we're going to turn to some reinforcement learning. We're going to try to reward AI systems, or these neural networks, these language models like event-to-event or seek-to-seek, for getting closer and closer to a story. So here's kind of a zoom in on the pipeline here, right? So we have these events or sentences, we'll call them events, right? We pass them through some sort of magic neural network, some cloud-like thing, and we get another event out. Okay, now the thing I didn't really talk about before is that event to event isn't actually generating an event. It's actually generating a distribution over outputs. And I'm only showing the verbs here, but basically you can think of it might produce many different possible events, one involving meeting, one involving killing, finding, admiring, driving, marrying, so on and so forth. Now we might, as a person who is trying to make a story using a neural net, we might say, well, actually, I want this story to be about marrying, right? But my model thinks that marrying is a very unlikely thing to happen based on what has happened in the past, the previous events. So what I need to do is I need to figure out how to make the neural network kind of reprioritize itself. So we need to ask, does this new event that we might choose, do any of these get us closer to the goal? And if it does get us closer to the goal, can we reward our neural network? Can we give it a better loss value and propagate that reward back through the neural network so that it learns over time to reprioritize its distribution, so that it's more likely to produce the outputs that we want to see because it's moving our story in a particular way. Okay, so that's the intention, that's the goal here, right? So we're not going to do anything particularly crazy. We're just going to produce rewards and back propagate those rewards back through our neural net so that it becomes more attuned to moving the story in a particular way. But there's a problem here, right? How do we know that an event is closer to the goal? Okay, so the problem that we really had to solve was, how do we know that we're actually have a story that's moving in the right direction? So to do that, we go back to the corpus, and we go back to the verbs in the corpus, and we say, well, let's actually plot out all these verbs. And we see that some verbs tend to be closer to other verbs. So if we want a story about two characters getting married, we see that certain verbs like discovering and amusing and seeming tend to be clustered around marry, and others seem to be further away, like resigning and appearing, escaping, converting, right? But they're close to discover. So, but you basically get is this kind of graphical structure of closeness of verbs to other verbs. Now, so the idea then is our neural network should get higher reward whenever it produces a verb that's closer to the goal. Unfortunately, this actually doesn't work, because if you say give a higher reward for getting closer to the goal, what does the neural network do? It learns just get married. Once upon a time, there were two characters, they get married at the end. That's actually not good storytelling practice. What we actually want to do is we want to move the system through levels or layers of verbs, right? So we can kind of think of these as a tiered system, right? Our target is in the middle. We have certain verbs that we hope to see right before we get married. We see certain verbs that we hope to see a little bit further away from being married, and so on and so forth. And what we want to do is we want to give reward to the AI system, not for moving to marry, but for moving from one layer to another. So if you generate escape, then I'll give you more reward for moving to discover. Once you get to discover, I'll give you more reward for moving to marry, and so on and so forth. And if we do that, we can in fact fine tune these neural networks to produce goal-seeking behavior and also kind of generate these plots like we've just seen. So I will let you kind of look at this horrible jumble of mess while I take a quick water break. Okay, so I get a lot of examples from Star Wars. We have good Star Wars plots. And you can kind of, if you make like reasonable guess about who the persons are, you can kind of see that these sort of make sense. And they end in the goals that we want. So the first one, we want some sort of, actually in both cases, we want a discovery of something. So we do have a story about someone finding someone in the first, and then someone learning about something, and it looks like some sort of spy caper in the second one. If we kind of squint and imagine what all these characters and crafts are, and explosives, right? Matter of fact, if I went for the full step and I generated the full natural language, we could put these natural language stories in front of people, and we can do some experimentation. So few things to observe here. One is our system now can achieve the goal at greater than 93% of the time. Interestingly, the perplexity that we talked about, which was the confusion index, goes down. Why is this? This is actually really interesting, right? This additional fine-tuning on these this graph of verbs was able to extract more knowledge from the corpus than the neural network could find through its standard word-level cross-entropy. So we actually ended up with a better, more predictive system from a perplexity standpoint. And most importantly, when we put these stories out into the wild and we asked people to tell us if they were have plausible ordering, or appear to be a single plot as opposed to a jumble of plots, or have local causality, what we find is the dark bars, which is our new improved system, was significantly seen to be more coherent, basically. So we have made progress there. The downside, of course, is that every single goal you have to retrain your neural network. Okay, but we're not done there yet. And I'll kind of explain why. Here's another output from our system. And I'll don't worry about the tuple crap on the left side. What you see is you have a story that says, well, let's get to two characters admiring or adoring, or someone being adored or admired. Okay, so what you see is this happens, right? But if you read through this, it still kind of makes these weird leaps, right? It's still kind of not totally coherent. How do we get to gathering in Hawaii to robbing the pack and adoring the party, right? It's still making these statistical decisions, and those statistical decisions don't always track particularly well with what the reader thinks is a good transition for a story. So with that, I'm going to kind of take us into what I think of as kind of the third phase of story generation. And we'll call these neurosymbolic systems. What I'm basically trying to do is say, remember when we had really good coherent systems? And then we went to neural networks, and then our coherence went to shits. Got really, really bad. We did some good things, right? We went to better technology, more robust technology that could do more without domain knowledge engineering, but we lost something. We lost the ability to reason about coherence. So how do we kind of reassemble all these things that we've learned over many, many years to build better systems? So how do we get to narrative coherence in these neural systems? And I want to kind of make a few observations here. So the first is that neural networks have a latent state in the hidden layers of the neural network. That is probably not the same representation that readers use. So remember, coherence is about perceptions, right? Why do I, as a human reader, not see these stories as coherent? Well, I'm probably thinking about the state of the world, the state of the characters, what the characters are doing in a very different way than the neural network. I don't actually know what the neural network is doing, but it's doing something inside that latent state, but it's probably not the same thing that I'm thinking about as a human reader. So there's no requirement for a neural network that the next event be related in any way that humans will understand in a neural system. And I think that is the fundamental thing that we've been missing up until now. So what do we know about narrative coherence? Well, we can turn to psychology again. Psychologists will actually tell us that humans do reading comprehension, and they track two things: causal enablement, so things that cause other things to happen, and character goals. So this character seems to have a goal, and these are the set of actions that they seem to be doing to achieve the goal. Now, causal enablement is actually something very specific here. It means some event 2 could not happen if event 1 had not happened, right? So, think about a story about, Sally killed John with the umbrella, right? Did Sally have the umbrella? So Sally could not kill John with the umbrella if Sally did not already pick up the umbrella. And so we look for these, basically what psychologists are saying is readers are looking for these connections between events that seem to be very causal in nature. And if they're causal in nature, then you can actually take any sort of story and you can decompose the events and you can build a causal graph that says, these are the events that rely on which previous events. You can see all the arrows are pointing upwards. Looks a lot like those theorem proving systems that we saw a long time ago. Okay, so maybe what we need to do is we need to track these causal relationships to build a model of what's going on in the story world that's going to be more similar to what humans are going to think of when they are trying to read stories, and then use these reader models to inform story continuations. Okay, so the classic diagram that we've been working with before: event goes into a neural network, you get another event which goes into the neural network again, and so on and so forth, is how we've been thinking about neural story generation with language models. Well, maybe what we also need to do is every time we see an event, we should infer what the reader is going to think about the causality of the different objects and characters in here. And then let's make a small little change. Let's say the decision of what happens next in the event should be a factor of what the neural network thinks should happen from a statistical standpoint, but also take into account the reader model somehow. And so the proposed change is to kind of merge these two layers, the symbolic and the subsymbolic layers, to make hopefully better choices about events and get more coherent stories. And I'll take you through this very quickly because I think I'm kind of getting low on time here, but I actually want to take you back to that old example about the hungry dog licking her lips. So with the initial prompt, let me kind of deconstruct what would actually happened in this situation, right? We had GPT-2, which is a very good language model trained on billions and billions of words of data, is able to produce a continuation of that particular prompt using statistics, right? And as it goes on, we're feeding this through GPT over and over and over again. So at any given iteration, what's really happening is we're taking the context, the words that we've seen before, we're putting it at GPT-2. We're sampling from that distribution. Remember, we're not actually producing words. We're actually producing a distribution and then sampling from that and producing the next set of words. But under the new paradigm, what we'd also, that's the subsymbolic part, we would also be tracking what we think humans will be thinking about, which is to say, what do we think humans will get out of the story that they've read so far? So who are the characters? The character 1 is a dog. The character 1 was watching his owner. The owner was eating. These are kind of things that humans might infer directly. And I've just put this into graphical format because we're computer scientists, right? Now, this is what the human might be modeling the story about. Well, we can take what we've just sampled, the next sentence, and we can say, well, what would the reader infer about what's happening next? So this next sentence says the character is a wolf and the wolf is dangerous. Well, this doesn't jive, right? So character 1 was a dog before, character 1 is a wolf. So now we have this disconnect between what the reader was thinking about the story and what the reader would think about the story if we made this progression. So this is not going to be a good progression from the standpoint of the reader. And we can identify that by doing some graph matching. So what do we do then? Well, here's the secret here, right? We're inside the sampler. So just go pick some different tokens and see if we can find the next most likely sequence of tokens to get a better outcome from the reader's perspective. So we're trying to guess what will be coherent from the reader's perspective. Very quickly, I'll just talk about how we do this inference. We're going back to VerbNet. And VerbNet, what basically, I'm not going to spend a lot of time talking about this, but basically VerbNet doesn't just tell us what our verbs are, but actually tells us semantic information about our verbs. So it tells us things like, in this particular example, Jen sent the book to Remy from Atlanta, that the book was in Atlanta, the book became no longer in Atlanta, and the book is now with Remy, right? So these are all things that humans will basically be able to understand just by reading this one sentence. And VerbNet is this great repository of all this semantic information, and we can basically mine it for inferences that humans are likely to make as they read the story. And these has location, sorts of things, they're going to look a lot like that graphical information that I just showed you. And to kind of cut to the chase, here's what stories look like when we generate from here. All right, so we prompt it with Christopher Attacks Harriet. I should mention that we're now training on a science fiction corpus, so everything is going to look very science fiction-y, right? Cybernet comes up, Cybernet is dead, the king is able to survive. Okay, so actually, how do we know this is a good story? This is not a great story. But what I can tell you is the story would have been worse. So the more probable thing that the AI system wanted to do was follow up the first sentence with, she shoots him with an object and he falls to the floor. Well, the system rejected that because neither Harriet or Christopher is known to have any objects, right? So no one has picked up a gun, for example. So that was problematic, and we can look at other examples here, right? So this transition here, the transition that the GPT-2 actually wanted to make was location 1 is able to escape and is eventually captured. Well, locations can't escape, right? We know that by looking at how this word is being used, location with escape. So we know that that's not going to be a good transition. It's not going to make sense to the reader. So we choose something else and we go on. Matter of fact, we can put these stories in front of humans. We can look at vanilla neural systems versus our new system. Our new system is in this orangish red now, and we see massive gains in people declaring that these are more coherent. They have more plausible order. They make some more sense. They seem to be a single plot as opposed to a bunch of random stuff happening all together. And that's a great thing. Doesn't just have to be this way. There are other ways of doing reader models. We're now exploring using common sense inferences, and so on and so forth. And I think what we're seeing is that this possibility that we can, in fact, track these stories at multiple levels, no matter what our inference technology is going to produce things that readers like more or understand more. And in the end, isn't that what we really want, right? We want things that humans are actually going to read. And so to me, this is a very important thing that we need to keep in mind when we do story generation, which is that we're not doing story generation for story generation's sake, but we actually care about who our readers are and care about what our readers are inferring or getting out of reading these stories. Okay, so I'm going to wrap up here. Just kind of a few thoughts going back to the beginning, right? So story generation, from my perspective, has been a very important lens on some of these core challenges of artificial intelligence. We're doing planning with language. Planning with language is interesting because language is a huge space to search through, right? Not only can we do things that make sense, but we can also imagine these science fiction sorts of scenarios, right? You can have laser swords that you might not have in the real world. So this goes beyond just pure grounded language. We have to think about our representations and our reasoning, how we reason over these representations. We have to incorporate common sense, because if you mess up the basic things that everyone agrees should be done in a certain way, your story falls flat really, really fast. It's very obvious when your system doesn't understand things that humans want the system to understand. We have to incorporate this theory of mind, right? We have to think about our readers and what our readers are thinking about as they generate the stories, and use that information to guide our system to make better choices, because that's what humans do. We think about our audience when we're telling stories. And of course, grounding our language in action, right? So making sure that things, again, this is basically just another way of saying the system has to actually understand what it's doing, because it's going to have to put what it understands into use. And when you put things into use, you know very quickly whether it understands or not. But of course, we care about those core AI challenges. We also care about building systems that work, right? So And we do this because we want to test whether our system actually does all these core AI systems, because we see it in front of us. We see it in a text. We see what works and we see what doesn't work. So we do care about AI challenges. We also care about making working systems that make good reading stories. In this kind of talk, I've kind of laid this out kind of somewhat historically, chronologically. We've seen that story generation, as with the whole field of AI, has gone through several phase shifts. We've gone from symbolic systems that had coherent and goal-driven generation, but we did that at the expense of knowledge engineering. We fixed the knowledge engineering by going to learning systems. We started to lose some of our coherence. This is very interesting from my personal perspective, because it felt like when we went to machine learning systems, we took a giant step back in the capabilities of our generation systems. We gained a lot. We don't always see what we gained because we saw the ability to produce more complicated models from data. Let's not sweep that under the rug. That was actually a really good thing, but we lost a lot of things that we knew how to do. And now we're kind of crawling our way back up, saying, all right, well, what are all the lessons we've learned through across all these years, through all the phase shifts, and how can we bring them all together to finally achieve some of these core AI goals, as well as real working system goals to make good story generation systems. Okay, and then to kind of leave you with the highest level points last, narrative generation is central, in my opinion, to many of the things that humans do on a day-to-day basis. So this computational narrative intelligence is going to be key to making real AI systems that really work in the real world. Story generation is one of those things. Story understanding is another part of it as well, right? And we can look at perspectives of kind of reuniting some of the cognitive perspectives of AI with the data-driven perspectives of AI, which I think is a very promising, compelling way to move forward. And ultimately, I think, humans want to see a little bit of themselves in the AI systems that they work with. And so I think when we talk about, the path to AI, whether you believe in, general AI or not, I think we're going to run into this question of stories more and more often. And we have a little bit of running start, but there's definitely a lot of headroom, a lot of space to do new and exciting things in this area. So hopefully I have compelled you that you should all drop your research and go run off and become story generation researchers. If not, I just hope that you've kind of enjoyed and seen this kind of interesting perspective on one way of doing AI and natural language processing work. All the things I've talked about, there's a ton of stuff, has required a lot of help and a lot of great people. Yeah, I'm sure you'll be running into these people in the next few years, as well as the generous funding sources, wherein I've managed to trick many funding sources in the United States into, allowing me to do crazy things like this. And I give thanks to all those people. And with that, I leave you with this slide, and thank you very much for being here. I'm sorry I couldn't be there in person. I'm sorry I couldn't see you and see your questions. Happy to have a discussion now with you. Thank you very much.
Great, thank you very much, Mark. And you hear the applause. It's under this applause on people's desks. We need to have mics coming through.
In my mind, it's
in your mind. You can generate a story where everyone's clapping. But yeah, we have a good attendance. We don't have any questions, although we had some people with clarification. So if you want to ask a question, you can click the Q&A tab in the video and type your question in there, and we'll see it, and I can come publish it there. I have a couple things to ask. We can just chat about that. And I'm sure you'll get people coming back and asking you about it after they look at the talk online as well. But yeah, fascinating. I was excited. You did like some great little things with the Snyder cut of Aladdin and the R2D2 alternate drinks thing. It's like, oh, I wonder what those come. I'm wondering if one of those from the Christmas special, Yoda trying to do something.
Oh,
never
yeah,
watched the old one, but I'll have to go.
It might be.
Because you'd see him doing that. But I mean, one of the things you were talking about was this reader model, the inferred reader model, sort of near the end that you're trying to, like the theory of mind of the reader. I didn't catch where you got that from. Is that hand coded, or are you learning that?
Oh yeah, no. I glossed over it in terms of time. The question is, where do you get the inferences of what the reader is going to think about your story. And this is actually kind of a big, hard problem itself. What we did is I don't say we cheated, right? But we found resources online. So in particular, I didn't have time to talk about VerbNet, but VerbNet is this big resource of semantic information about verbs. So basically, it has every verb in English and how it tends to be used in sentences, and it has information that says when it's used in this particular way. When we look at the syntax of how it's used, then you can also infer additional information. So I'll just kind of come back here to some of these details. So VerbNet will tell us if you take this sentence, Jen sent the book from Redmond to Atlanta, and you look this up in VerbNet, it'll tell you that the verb is sent. That's the easy part. That's the part most people kind of look at. But it also tells you that in this grammatical context, there are things that we can know about all of the entities in this. All right. So we know that there's Atlanta is a location. We know a book is a concrete thing, meaning something that can be held, right? And then we know that Jen is some sort of agent, and agents tend to be animate or possibly organizations. But more than that, we know that there's some movement, right? So the book, we can infer that the book was in Atlanta. Jen was the person who caused some motion to the book for it to move to a different location. That the new location at the end of this sentence was, it's in Remy, whatever Remy is, right? Remy has it. There's kind of this notion of has here. And it wasn't in Atlanta anymore, and it can't be in more than one place. So what we basically do is we mine this repository and we make some inferences over the semantic information that's being given to us, which look a lot like preconditions and effects. All right, we say that we know that the book was in Atlanta. We know that the book is no longer in Atlanta. Right. So if we get another sentence that comes along and it says the Atlanta police burned the book, right? We can say actually no. The book is no longer in Atlanta.
Right.
Yeah. So that's no good, right? But if we say Remy reads the book, it's like, okay, the book is in Remy, and book are co-located. So that's probably a good progression. Right. So this is how we're doing the inferences there. Basically, we're using the fact that a bunch of smart cognitive scientists and linguists have compiled all this information for us. And pop through here, right? There are other ways that we can do this inference. So lately we've been looking at neural networks that do inferences. So there are neural networks like one that's called Comet that I like a lot. It's a common sense inference system. So it's trained to say, if you give me a sentence, I will infer a bunch of facts. Very similar to what we saw from VerbNet, right? So if person X gives person Y a pep talk, we can infer that person X was wanting to be helpful, that they'll be seen as smart, others will feel grateful, right? These are also things that we can infer just from that sentence.
Right.
And again,
these are all logical,
yeah, and we're making the assumption that these are more or less what people might also be thinking when they read the sentence. So we don't actually know what's going on inside the reader's mind. We're making guesses. Right. And what I was just kind of trying to convey very poorly was that, there are multiple ways of doing this inference to build these reader models.
But this way seems to be one where you're not really adding too much more bias beyond that, trying to come up with particular, approach. You're just saying, well, logically from the language, here's what could happen next. These are all the possibilities that make sense linguistically.
Yep. Yeah. So great. It's a very linguistic perspective. Had a great PhD student, Laura Martin, who is also a linguist there. And I also say, like, we always do this thing where we start with the simplest thing, right? Can we do something that we could do, without building an overly complex model? Then we figure out where the system breaks down and we build a more complicated model.
Yeah, on that makes sense. You want provable results, right? And that show that there's progress. Cool. So we have a question from the audience, from Ellie. I don't know if you can see the question, so I'll read it out.
I cannot, so thank you.
Okay. I'm curious if there are any researchers that you know of that work on generating stories with expert crowdsourcing, for example, with professional authors.
Yeah, great question.
Download Stephen King into your database.
I have, no, I don't know of anyone who is working with expert authors in story generation right now. So my own, I have worked with expert authors in the past, and I chose not to pursue that route, and I don't want to say anything bad about authors. They do great stuff, but what we often find is that experts are not always the best at explaining what they do. Right. So asking Stephen King, how he makes stories, how he's such a good writer, I think you'll find they would have a very hard time kind of breaking it down to the level of detail that we need to make computational models. Right, because there's this huge divide between I have a neural net and I can train on something, and Stephen King thinking about suspense plot devices, right? So that was not a particularly useful personally. What I found was more useful was talking to cognitive psychologists. So you can see all through this talk, I kind of refer back to what cognitive psychologists say about them, because they're very good at breaking down these cognitive processes into smaller and smaller steps. And the smaller those steps are, the more I can think about a piece of algorithm that corresponds to that piece of cognitive process. So that is where I have found the most value. I don't want to rule out working with experts. It's just I found a particular route that kind of worked for me.
Right. And kind of a related question then from Olga. Do you see story generation systems more as standalone systems or as tools for assisting human writers? So how do you see the role of humans in hybrid systems?
Yeah, no, also a great question. Obviously, I've been focusing on generation as standalone systems. I'm particularly interested in the question of how far we can push our computational theories in this creative space. So I do want to see personally standalone AI systems. But obviously, there's this huge application area of co-creative software, where humans and AI systems are working together. And I think co-creative space is really interesting, because I think a lot of us imagine wishing we could do things that we're not actually skilled at. So I personally can't play a musical instrument, but sometimes I get a tune in my head and I think it's kind of new, but I couldn't actually make it real. So I would always wish that the people in the music generation space would hurry up and get systems that I can play with around that.
You just hum it and then they create an orchestra like it. Yeah, that'd be amazing.
Yeah. Now in story generation is a little bit different though. Humans are already pretty good at making stories, right? Even by the age of 5, you can tell not bad stories. AI systems are, are they as good as a 5-year-old yet? I'm not sure we can really say that. And until they are at the same level of creative capability as humans, it's unclear to me how much we can help versus hinder.
So how about creativity? Because there's a couple questions on that. Like, is it possible to get creativity into these systems? Like, what would be needed to make that possible?
Yeah, well, creativity is, there's lots of definitions and theories of creativity. One is blending of concepts, right? So, or the ability to make these leaps or bounds, right? To go from concept 1 to concept 2 that are actually related, but in a non-obvious sort of way. So we can build systems that are creative. I think we need better theories of what creativity is and how to computationalize that. I think we have more progress in the visual space right now than the linguistic space of that. Right now, a lot of creativity is just randomness. So it's kind of accidental novelty, accidental creativity. That story about the wolf is actually kind of creative. There's lots of interest.
Well, that's what I was wondering with the wolf, yeah, because did it know that dogs and wolves are kind of related in its model anywhere? Or it just did it because wolves were dangerous?
Yeah, I'm kind of like reverse engineering what's going on here, but I would infer that wolves and dogs are semantically interchangeable. They're semantically close to each other. And so if you include dog and blood, a word that's close in semantic space is probably wolf, right? It's the old king minus queen plus king minus man plus woman equals queen. That kind of idea.
Yeah, concept space where they're similar and you just move through this space. But I guess, so that's possible, right? It has encodings of the way words and concepts relate given what it's seen and text it's learned, so.
So, but the potential is there, right? So the potential to make this linkage between dogs and wolves, maybe the thing not to do would have been to swap the notion of dog and wolf. And by the way, it never actually said there's an entity called a dog here. But to say a dog acting like a wolf is actually a really interesting idea. So it accidentally got close to something kind of creative. The problem is it didn't understand, it wasn't an intentional leap, right? So the question is, can we make these controllable leaps in, or blends between different ideas so we can manipulate concepts in interesting ways? I think it's doable, right? I think, but the language model itself is not trained to do that. So we're going to need, in my opinion, something that's external that helps guide that process or constrain it in particular ways.
Oh, okay.
I mean, rough ideas on creativity here, right?
It's obviously a hard thing. I mean, if we have, general artificial intelligence, there's some of the things that are, more doable. People used to think, facial recognition and playing chess and all these things were intelligent. We've given up. So now it's like driving cars and, playing video games. But writing stories creatively is probably one of the hopefully one of the
and I do think creativity is going to be an important aspect of making systems that we can actually communicate with, right? So I think of Siri.
Oh, okay,
right? So Siri is not a very creative thing, right? If I can think of a plan and I can break it down into finite steps and I can ask Siri to help me with each one of those steps. But if I can't think of a new way of solving that problem, then Siri definitely is not going to think of a new way of solving a problem. So it would, or even worse, I think of a creative way of solving a problem and Siri is totally lost. Like, how did you get to, this step in your plan?
Right.
So
yeah, so
it's going to be an important problem. We're not quite ready for that problem yet, but I think down the road, I see it becoming important.
Okay. Yeah, because there was 1 or 2 questions about that now, about insights regarding memory mechanisms and story generation. So how do you remember long-range dependencies? You had a bit of this rewarding it to hit certain checkpoints in a story, but does it have a lot of memory to remember? It's like, oh yes, I've checked off, I got to the second, denouement of like the relationship, now I need to do this. Like what part does memory play?
Yeah, we didn't really look at that problem. Right, so yeah, you might, now you're talking about goal chaining, right, and having goal hierarchies.
I guess so, yeah.
Right, that's going to be an important part, right? So we're still telling really short stories with these systems, but longer stories are going to have to research. That is open, so if anyone wants to go and take that one on, go for it.
Sometimes the people are asking questions like, oh, what's next? What's next? So yeah, there's a lot of great questions here. We touched a couple there. Somebody else had one just about, what about the effect on the reader? So in terms of this going back to the goal of generating stories, you could just try to convey information, but what about emotion, the effect, the impact on the reader? Are you trying to make them sad or stressed or happy?
Yeah, I love that question because I don't know the answer.
That's right, that's even harder, yeah.
Right now, like, we're doing very simple stuff. Our goals are things like princess escapes, or 2 characters meet, or 2 characters get married, right? A very kind of like objective in-world sorts of things. Happily ever after isn't even something that we really know how to encode yet. But no, the question is right. Often we don't tell a story just because I want the princess to live happily ever after, but I actually want the reader to go on this emotional trajectory, right? I want them to feel sad in the middle and then happy at the end. How do you encode those emotions into something that an AI system can reason about when it's thinking about either words or now maybe, knowledge graph, like, connections between symbols, right? Okay, so
trained it on stories of that type, that all horror stories are very good stories that create this effect. Would that be sufficient?
Well, I mean, I think part of it, right? But also, like, if the patterns are shallow, not, right? So I like to think of the example of, the knight slays the dragon. Is that should we have a positive affect? Should we have a negative affect? I mean, oftentimes the dragon's the monster, but if the dragon's the hero, right? That's a very sad thing. So, if our pattern is shallow and says dragons dying is sad, I think that's not really what's going on inside the human's mind. They're looking at the longer implication of these things.
Hero versus, the concept of what the character is in the story and what's happening to them. But I wonder with your reinforcement learning approach, if there'd be ways to have the objective function be not just going through the plots, but about like what the reader's feeling while they're reading that. Like you'd need data or a model of what you'd expect a reader to have. So that's something to create. But
Yep. No, that's where I want to go. because I think now that you have a reader model, can you take it one step further and says, what does this reader model mean from an affective standpoint? Right. So a few years ago, we did some investigation of suspense, and suspense is this really complex cognitive phenomenon where you have this anticipation of a negative outcome for a character that you like, right? So James Bond is going to die, and then you get James Bond out of that situation, and then we feel relief, right? And there's this kind of anxiety, cathartic release kind of pattern on here, right? So can you look at, I don't think you can look at the patterns of inside of a language model and correlate that to this pattern of anxiety and catharsis, but maybe at the symbolic or more abstract level, maybe we're moving in the right direction. So I hope to be able to do this in say the next 5 years or maybe sooner.
Challenge. Cool.
But there's a lot of space to work in there as well.
For sure. I think just one more question. TJ just posted one here, and it's really good. How's the problem of human bias addressed with such models? So you got news generation being generated certain sources and being biased towards the writers or the public. What's the risks or challenges for that?
Yeah, no, great question. This comes up a lot. I've not in this work. I have not done looking at bias. Our language models are totally biased, though, right? I would say my students get sexually harassed on a weekly basis by GPT-2.
Oh, by the model, because it just it said that it does that by default. Yeah. Right.
So there are huge issues of biases in stories. Everything from who the bad guys tend to be to sexual content, political content, racial content, so on and so forth. I'm not working on anything that I'll say is immediately deployable without these risks manifesting themselves and manifesting themselves in ways that I would not feel comfortable with. That is not an excuse. I also have work. So another part of my lab works on AI safety, and we have been working on fine-tuning language models to reduce what I call non-normative language. So if we don't want to talk about racism, it's not just the words, but how the words are used, right? So if I want to make sure that certain concepts do not come up in our language models, how do we teach in a machine learning system the notion of appropriate context and inappropriate context? And we're working on doing fine tuning there. So I do have another paper somewhere else where we look at reducing the non-normative behavior in language models. And then these two kind of threads run in parallel, right? So at some point they need to come together so that we have safe stories.
Well, but it's a huge same systems. Some like plot shaping and story generation, like direction things could, I guess, be used in the same way to direct it away from the biases that are in the mainstream data sources that we have, right? Yeah. I mean, I personally do not trust any of the pre-trained language models to not put something inappropriate at any given time, and largely because it doesn't understand the effects of the words on the reader, right? Yeah, and so go by correlations and frequencies, right? So
yeah, and it comes down to using sexualized words or gender words or racial words, but even like humans are really good at innuendo, right? You can basically take any innocuous phrase and think of a dirty way to use it, right? So, the more our AI systems can understand the implications, and this does get back to the language models, but also that I've been looking at, but it also gets back to the reader model, right? So, like, we're not ready to do this yet, but like affect, right? Can you take it to a next level above the semantics and say, is this something that, how does this make you feel, right? How does this kind of match our expectations of what is culturally appropriate or inappropriate? Huge issue that needs to be worked on. Absolutely.
Also do there. Great. Well, so like I say, that's the direction things are moving, but there's lots of interesting progress. So I think we'll wrap it up there. And thank you, Professor Riedl, for a fantastic, interesting talk. Lots to think about. And,
no, thank you. Thank you for all the really great questions. I really enjoyed those questions. You're thinking very hard for early in the morning.
That's right. Great. Okay. Well, thanks a lot, and hopefully I'll talk more in the future.
Okay. Thanks, everyone. Have a good day. Have a good week.
everyone, and see you all for the next talk. We'll have another, next seminar will be on March 9th, Thomas Dietrich, with talks on machine learning and reinforcement learning. We'll have more information going out to you soon. See you all, and thanks for attending.